Okay, so last video I ran out of time, so I'm going to be moving faster this time, hopefully. Okay, so here's our graph. Blah, blah, so we have that. From the graph compares hard steel to soft steel, which can be described, soft steel can be described as stiff. No, soft steel is less stiff than hard steel, because hard steel is a higher gradient. Okay, that stiffness is the gradient. Strong. Strong is how much stress it can take before it breaks. Hard steel is stronger than soft steel. Wrong. Brittle. Brittle is how far along the strain that it goes. If it's really short along the strain, it's really brittle. If it goes a long way, it's very malleable or ductile. So, no, soft steel is less brittle. Hard steel is more brittle than soft steel. Soft steel. Ductile. It goes a long way along strain. It's more ductile. D. Okay, 1 minute done. Which one of the following statements indicates that hard steel is stiffer than soft steel? So, as I said before, stiffness is related to gradient. You can watch the earlier videos to check that out when I explain everything in depth, but stiffness is gradient. And gradient is Young's modulus in a stress versus strain. So we're looking for gradient or Young's modulus. The gradient of the stress versus strain is harder for hard steel. D. Which one of the following statements about toughness is correct? So toughness is energy per unit volume. Or, in a stress versus strain graph, it's the area under the curve. Okay. Soft steel is harder than tough steel. Is there more area here than under there? I think so. So that's probably right. Hard steels, nope, that's probably wrong. They're not equally tough. You don't need to know the volume because toughness is only related, is independent of volume. It's to do with the stress-strain graph. Again, watch one of my earlier videos to check that out. But that means soft steel is tougher than hard steel. Okay, 2 minutes is up. And how many questions have to go? 4 questions. 30 seconds a question. Oh no, I got 3 minutes left. Okay. So a rod of soft steel, initial length of 10 meters. So write that. That helps so much under tensile strength. The strain produced by the stress is, okay, so strain equals 1 times 10 to the negative 3. Okay, so we're trying to look for the length. Okay, so when it says the length of the rod, we have to look at the original length and the change in length. Okay. Now, strain. Always write down what strain is before you continue. Easy. We have our original length already. We're looking for this, and strain can give it to us by multiplying these two. Therefore, delta L equals this times this, which gives us 1 times 10 to the negative 2. Awesome. Okay. So, now, this is under compression or tension? Tension. So it's getting longer. So it's 10 plus 0.01. D. Yeah. Okay, which one of the following best gives estimates of Young's modulus for hard steel under tension? So Young's modulus is the gradient. Hard steel under tension. This is under tension. So let's take some random point here. And take that point. It's about 400 up. Times 10 to the 6, it's about 2.25 down times 10 to the negative 3. So we just divide them by each other. $178 times 10 to the 6 times 10 to the negative 3. I'm just doing the shortcut way. It's supposed to be plus 3. 0.78 times 10 to the 11. But you can just use a calculator to do all that. You can just divide it using a calculator. So they say about 1.6. I had 1.78, but I think they're going for 1.6. Also, just so you know, I'm doing everything through my phone, so I can't actually see the piece of paper. So it's a bit hard for me to write. Okay, so length, 2 meters, cross-sectional area equals 8 times 10 to the negative 5. Made of hard steel. This rod is placed under tensile stress. Force on area equals 200 times 10 to the 6. Okay. Which of the following is the best estimate of the force that must be applied? I'm going to go over time. I'm sorry, guys. To provide this stress. So, we want force. We have force over area. We just multiply these two together to get force. 1600 times 10 to the 3. Or 1.6 times 10 to the 6. Because I'm using the point from here. 1, 2, 3. So I add 3 zeros. and it's not there. Maybe I put something wrong. Oops, that's 5. It's 5. Oh, sorry, that's 1. And then that becomes 4. There. I blame my camera because it's hard to see. Anyway, finally, a stress is applied to the cylindrical rod. Stress equals force over area, 100 times 10 to the 6. Strain equals 1.25 times 10 to the negative 3. So the key is I'm not thinking at all, I'm just writing things. The strain energy. Okay, so we know stress, we know strain. We want the area under the curve. The stress is 200, the strain is that. So we want the area under there. So they kind of told us what the stress and strain is. So this is the base and the height of our triangle. Height, base. I want the triangle, so I just go half times base times height. Half times 200 times 10 to the 6 times 1.25 times 10 to the negative 3. Everything's kind of bright now, but I'll try and do it on my calculator. I won't show you. I messed up. Because I'm not very good with calculators. Don't be like me. Be good with calculators. That's my answer. 125,000. Or 1.25 times 1, 2, 3, 4, 5. 10 to the 5. Closest one is 1.3 times 10 to the 5. Okay, so that's how you do stress strain questions. Cheers.